Hey guys! So today we're going to talk about the last aspect of Lewis structures that we really need to understand, which is something called resonance. So we're here. So resonance is a property of certain Lewis structures, not all of them, and it really comes up if you ever go into biochemistry or organic chemistry. There's a lot of resonance that you need to understand, but we are expected to know when this happens and kind of some ideas as to why. So resonance, first of all, can only happen when a double bond is next to a single bond. That is what has to be there. Doesn't mean it always happens when that's there, but pretty much if there's a double bond and a single bond next to each other, in a lot of cases, resonance can happen. So I'm going to show you an example, and I'm going to show you an example that is O3. O3 is actually ozone, so we talk about the ozone layer. They're talking about O3 molecules in the atmosphere. O3, we're going to draw the Lewis structure, so a little bit of a review. Step 1, we're going to count the valence electrons. It's pretty easy for this one. Each O has 6, and there's 3. So 3 times 6 is 18 valence electrons. All right, so first step, now that we have our valence electrons, is to connect everything with single bonds. And now we try to make everyone happy. So there's different ways to do this. I don't know which one you prefer at this point. You can use the electrons and spread them out, or just put all the electrons and see if the number matches. But we have 18 valence electrons we've used up. 2, 4. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Now you'll notice, make these guys bigger, I always forget. You should notice that one of these O's is not happy. Which O is unhappy? This oxygen only has 2, 4, 6 pairs on it. That means it is not happy. We do not have enough electrons to make a single bond work. So what we're going to do is add double bonds. Now, I recommend whenever you add a double bond, you take out all your valence electrons, add the double bond, and re-put them out to avoid the problem I had that last time where you forget ones that you're supposed to take out. All right, so we had 18 valence electrons. We're going to try one double bond, not both, just try one at a time. If that doesn't work, then we try another one. But I was only 2 electrons short, so my guess is one is going to work. So we're going to put in another bond. Now we've used up 6 electrons. This guy already has 4, so it needs 2 lone pairs. This guy already has 6, so it needs 1 lone pair. So we've used 2, 4, 6, 8, 10, 12. And this guy needs 3 pairs, 14, 16, 18. All right, so Lewis structure for ozone. Now here's a question. What if it looked like this instead? Which one's right? We can't use formal charges for this. They'd have the exact same formal charges. It's the same thing but flipped over, except it's not. Because if you think about these as, say this is oxygen number 1, 2, and 3, the question is, do we put the double bond between oxygens 1 and 2, or between 2 and 3? Now, in reality, actually, what's interesting about resonance is that the correct answer is not one or the other, but a combination of both. So what does that mean? That means the actual structure has like half double bonds on both sides. It's a combination of the two. So there's 2 ways to write this. If you want to write out each structure, that's fine. What you do is you put brackets around each one with an arrow in the middle. Usually they're side by side. It just didn't work out on the board. So it'd be bracket, arrow, bracket. Or what you can do is do these double bonds, these dashed lines that show a partial double bond. So really, if we have one single bond and one double bond averaging out, each one of these is exactly halfway between a single bond and a double bond. All right, so in this case, this would be like the resonance structure with our electrons on it. Like that kind of. All right, so they're halfway between a single bond and a double bond. Now, if we have something, for example, like NO3, NO3 looks like this. I'm not going to go through the process. If you want to learn how to draw this, you can go through it. But I'm going to show you. NO3 has three options. That's one option. Can you guess what the other two options are? If you guess that that double bond just moves around, you'd be totally right. So the other options look like this. I'm not drawing the dots on the other ones, but you can imagine that. Oh, and this is NO3 minus. I should have said that. If you're ever writing an ion for Lewis structures, pro tip, and we'll talk more about this later, ion, the charge goes outside. So negative. 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 And to be really accurate, you would need to draw the dots like you did here on both of these structures. But you see these double arrows that go between? That means all three of them are technically correct at the same time. Now, what this means is on the last one, in O3, each of those bonds was halfway between a single and a double bond. But in this case, they're actually not quite halfway. Do you think they're more towards single bonds or more towards double bonds? Well, the answer is there's one double bond and two single bonds in each one. So they're actually closer to being single bonds than double bonds. When we're talking about partial double bond character, you kind of average out the three. So if we have 1 plus 2, like the last one, we get 3, you average them out by 2 bonds, we get 1.5, 1.5 bonds on each one. Now for this structure, we have a single bond, single bond, and a double bond in each one. So 1 plus 1 plus 2, single, single, double. We add those up, we get 4 divided by 3, we get 1.3. So technically these are kind of 1 1/3 bonds. And in the O3 molecule, they are 1.5 bonds. So this would be for like O3. This is for NO3 minus. So as you can see, this resonance allows us to have kind of weird half bonds that are halfway or partially between single and double bonds. Now we'll talk a lot about how that bond affects certain things later, because certain bonds are stronger than others, certain bonds are longer and shorter than others, and this is going to come back into play. Single bonds are actually the longest bonds, with triple bonds being the shortest. But partial bonds are then partially between the two. So you can use that to kind of explain why something might have a longer or shorter bond length than something else. We'll talk about it a little bit more later. The key for resonance is that these three things are happening at the same time. So each bond gets partial character and looks like this. Weird half double bonds on each one. And that's resonance.